Perfect. All right. Welcome and good afternoon or morning, depending on where you are. Welcome to the second ARUNA monthly seminar series. We're here to highlight research being conducted across the ARUNA network. As a reminder to everyone and myself, this presentation is being recorded and will be posted online for future references. You can find a link on the ARUNA website. If you or somebody you know would be interested in presenting at one of these seminars, please reach out to your ARUNA representative or myself. Today, we're very pleased to have Dr. Louis Varriano, a postdoctoral scholar at the University of Washington. He received his PhD in 2023 from the University of Chicago, and he'll be talking to us today about the legend neutrinoless double beta decay experiment. With that, take it over.
Thanks, Sean. Yeah, so I'm gonna tell you about Legend in case I think ARUNA labs do a lot of beam-based nuclear physics in addition to other things. So you may or may not have heard about Legend, which is a neutrinoless double beta decay experiment. So I thought I would tell you a little. Next slide. I thought I would tell you a little bit about what the search for neutrinoless double beta decay looks like, in case you're not familiar, and then I'll talk about what Legend is doing to do that. And then I'll talk about what we here at the University of Washington and SENPA are doing to sort of support that effort with our tandem, which is why we're part of the ARUNA network. So as you probably know, we have a bunch of open questions in particle physics. We have a bunch of open questions in particle physics. Some of those questions are, what's the origin of the matter-antimatter asymmetry? Why do we see so little baryonic matter in the universe? Is baryon number minus lepton number B minus L a true global symmetry in the standard model, as in the standard model, or is it broken? Which is one of the questions that we're trying to answer. We'd like to know what the origin of the neutrino mass is. What's the mass mechanism? What's the neutrino mass hierarchy? And then everyone's interested in what is the energy scale of the new physics, assuming that there is some new physics out there. And so neutrinoless double beta decay or zero nu beta beta is one of those searches that can help us answer these questions. So we'll get information, if we observe this process, we'll get information on the neutrino mass hierarchy, the origin of the neutrino mass, this baryon minus lepton number non-conservation. And then we can even get information about the energy scale of the new physics, and sort of all of these questions. So if you're not familiar with neutrinoless double beta decay, I think all of us are familiar with beta decay. And so double beta decay is just two simultaneous beta decays. This process is extremely rare, as you can imagine. And in most nuclei, it's not observable just due to the fact that beta decay would dominate kind of the decay rate. So we can really only observe this two neutrino mode in nuclei where single beta decay is suppressed due to like large angular momentum differences, or if it's energetically forbidden. So in the diagram I have down here, if we look at the binding energies for germanium-76, which is the isotope I'll talk about today, single beta decay is forbidden. And so instead, we can only undergo double beta decay to selenium-76. And so this is one of the 30 or so isotopes that you can actually observe double beta decay or double electron capture. So the lifetimes of double beta decay range from 10 to the 18 to 10 to the 24 years. So that's a really long time, especially on the scale of like a beam-based nuclear physics experiment. And so that means that the kind of experimental design is very different compared to a lot of other nuclear physics that people do. And so in these decays where we have this two neutrino mode, we can also look at we can search for this zero neutrino mode, right? So there's a bunch of different proposed mechanisms that could mediate zero neutrino double beta decay. This is this light neutrino exchange, kind of the most simple, most popular one that people talk about. But in reality, you can have any sort of a black box here and put whatever new physics you want inside of that model. But for some of the parameters I'll talk about, they're usually related to this light neutrino exchange because it's a simple, popular model. So why again is this neutrinoless double beta decay interesting? You've probably heard about whether the neutrino is a Majorana particle, if the neutrino and the antineutrino are the same particle or have some overlap. And people would say that it's kind of natural to assume that they're Majorana-like. That's because, they're leptons, they have no charge, they're kind of weird already. Why shouldn't they be Majorana-like? Uh, so that's one sort of popular hypothesis. Um, the other thing I already mentioned is that this baryon minus lepton number would be violated, which would be an important breaking of the standard model, this accidental symmetry. Majorana mass would be shown to be non-zero. That's the same thing as saying that the neutrino is its own antiparticle. And then, as I mentioned, we can get hints about the scale of the underlying physics. So one of the other searches or experiments you might be familiar with on the high energy side is something like ATLAS or CMS. These experiments at Large Hadron Collider, they're searching for physics in the tens of TeV, hundreds of TeV range for like new gauge bosons or mediators. And in fact, we're sensitive to that sort of same scale depending on the operator you put in for whatever um, neutrinoless alpha beta decay mechanism you want to propose. So we're also looking at operators on the tens to hundreds of TeV scale in sort of that like interpretation, depending on the model. So for these different isotopes, there's obviously a lot of nuclear physics that goes into comparing them in terms of this like particle physics sensitivity that we're really interested in. And the nuclear matrix elements that I'll talk a little bit more about are really important for allowing us to compare across different isotopes. That's also really hard physics to compute these nuclear matrix elements. So you've probably heard a bit about that before. And so there's a wide range of predictions for these nuclear matrix elements in these different isotopes where we observe 2 neutrino double beta decay and search for 0 neutrino double beta decay. And so these are some of the 4 most popular, 4 most sensitive isotopes that the community has so far, along with some of their experiments. And you can see here that Legend is the experiment I'll talk about. This experimental program is, in terms of this M beta beta parameter, which is coming from this light neutrino exchange, we are, sort of sensitive in competition with these other isotopes. But the most sensitive limit, depending on the nuclear matrix element, is coming from xenon-136 right now. But hopefully Legend will catch up as we're data taking in the next few years. Okay. So how do we search for neutrinoless double beta decay? We're primarily searching for a peak at Q beta beta. And this is because if you take a look at the beta decay spectrum, since this is like a 5-particle decay, right, we have this broad energy spectrum coming from the total energy of the leptons and the recoiling nucleus. And that's spread out over, all the way up to the Q value and down to 0. And the phase space near Q beta beta is really suppressed, basically. So we have a small probability of being close to Q beta beta. But in our 0 neutrino mode, the neutrinos aren't carrying away any of the energy from our detector. And so we can collect the full energy of the decay from the 2 leptons and the recoiling nucleus. And so we're looking for basically a peak at Q beta beta that's separated from our 2 neutrino energy spectrum. And that's kind of the signature of the neutrinoless double beta decay that we would see as a full energy collection there. So in order for us to collect that full energy, we want a few things, right? We need a large mass to get enough atoms because we're looking for half-lives that are, orders of magnitude larger than the age of the universe. We need a really high efficiency, so that way we don't miss the signal. That often means that we're going to use this sort of source equal detector paradigm. So the isotope that we want to measure, we're going to use as the detector. So for, in Legend, this large enriched germanium experiment for neutrinoless double beta decay, we're using germanium-76, and we're using germanium detectors that are enriched in germanium-76. So the source is the detector. That's not the only paradigm in the field, but that's one of the common ones. We also need really low backgrounds because we don't want other events to have the same energy, basically. I'll talk more about that later. But we need to, make sure that the events we're seeing are coming from the signal because they're going to be so rare. So Legend is this experiment that's located in Italy at Gran Sasso National Lab. This experiment is located underneath a mountain. So it's inside of this tunnel that's a highway with a lab that's been carved out to the side. There's lots of experiments here in neutrinoless double beta decay in dark matter. So you've probably heard of some experiments that are located here. But this is a nice place because we have this really tall overburden of rock that shields the experiment from cosmic rays, which would be one of the backgrounds. I'll talk more about the construction later. And so it's also convenient because we get to go to Italy, we get to go have a picnic on the top of the mountain, make sure that it's still there, our muon veto is still working. So that's a lot of fun. All right. So this is a little bit more on kind of the signal that we're looking for. So for this light neutrino exchange mode, in order to relate it to this Majorana mass that we're looking for, our signal, the number of counts we get basically is proportional to kind of this expression. And the important terms are our efficiency, our exposure, that's how many atoms and how long we watch them. These nuclear effects from our phase space factor and our nuclear matrix element. And then kind of these put together give us this neutrinoless half-life, which is kind of the parameter that we measured, right? And usually we're putting an upper limit on that because to date, no one has observed like a statistically significant neutrinoless double beta decay event, right? So the problem I already mentioned about backgrounds is what if we have backgrounds that are sort of covering this peak and hiding it? That's going to impact our sensitivity. That's going to impact the kind of limit or sensitivity to the neutrinoless half-life we can place. And so this is just a plot. I won't, just to mention, basically, we want to be kind of in this background-free regime. So if we have essentially no events covering our signal, that's where we're going to be most sensitive to a signal that appears there. And more importantly, we're going to be linearly sensitive in time. So instead of having like square root of number of counts, our sensitivity growing is that, we're actually going to be linearly sensitive. And so that is obviously more effective from an experimental design. You can imagine that these experiments are expensive because we need enriched isotope that's usually not the highest natural abundance. And so making good use of our detector material makes these experiments a lot more feasible. All of that's to say that we need really low backgrounds so that way we can observe this peak without any sort of covering. Okay, I'll skip this for now. But basically, I just want to point out that there's kind of this trinity of different detector signals you can read out. I guess I'm not skipping it. But and usually experiments are designed to take advantage of multiple channels. And that helps you discriminate between signal and background events. And so these are sort of some of the double beta decay experiments that are ongoing or planned. And just kind of clustered into the signals that we're looking at. So for Legend, for example, we're mostly interested in the ionization, so the charge that's deposited in our detector, but we also use scintillation light in order to suppress background events. I'll talk more about that. Okay, so Legend is, I already mentioned, we're using these high purity germanium detectors enriched in germanium-76. We deploy these detectors in high purity liquid argon, and that's because liquid argon is a scintillator. So if we have any sort of gamma scatter in the liquid argon or other energy deposition in it, we'll get a signal from light that is telling us that that event came externally from the detector, right? It's not this 2 neutrino, it's not the 0 neutrino double beta decay that we're looking for. It's probably a gamma, a Compton scatter, some other event that deposits some energy in liquid argon and some energy in our detectors. So this is a really powerful technique for us for rejecting backgrounds. We also need really good energy resolution. We'd like this peak to be kind of as sharp as possible. And we also don't want the 2 neutrino spectrum to cover the 0 neutrino spectrum if our energy resolution weren't so good. And so our detectors have something like 0.1% full width half max resolution at Q beta beta, which is about 2 MeV. And that leads us to basically get a nearly background-free search in Legend. So this is our background goal in sort of these typical units of counts per keV kilogram year. So basically kind of number of counts covering our signal as a function of exposure. Okay, so Legend just had our first physics result published earlier in January. We didn't observe neutrinoless double beta decay, but we were able to incorporate the relatively small exposure we had into this global germanium-76 half-life limit. And so the half-life on germanium-76 is greater than 1.9 times 10 to the 26 years, which is very long. You can find more details in the paper if you're interested. And then this is sort of the energy spectrum of events that we got from this recent paper. And you can see after we do kind of all of our background rejection and our statistical analysis or unblinding, we're left with only 11 events that, across this really, 200 some keV wide region, with one, and it just so happens that we have one event right near Q beta beta that's kind of impacting the limit we could place. This event isn't statistically significant in terms of like being a neutrinoless level beta decay, but it does impact our sensitivity, which I don't think I show in this slide, but you can ask me later. Anyway, so this is sort of the experimental program of Legend. I'll talk a little bit more later. The predecessor experiments were Gerda and the Varriano demonstrator. They were looking for discovery sensitivities on the order of 10 to the 26 years. Legend 200 should reach a discovery sensitivity of about 10 to the 27 years, so we have a ways to go. And then the next generation experiment, Legend 1000, wants to reach 10 to the 28 years, and we'll cover the inverted mass hierarchy kind of regime. Okay, so this is what Legend 200 looks like. We have a big water tank. This is a Cherenkov muon veto. So any of those muons that do pass through the mountain with some energy will give us a Cherenkov signal in this water tank, and then we can veto any events that happen nearby, which is good. And then inside of that water tank is a liquid argon cryostat. It's quite large. And then inside of that, we deploy our germanium array, which is this about 1.3 meter long array centered here. Legend 200 has up to 200 kilograms of these detectors. This is what they look like. So you can see these bare germanium detectors on strings. You'll notice that there doesn't seem to be much supporting hardware. That's because we have a really low background experiment. So we want as little mass of external stuff near our detectors as we can. We have these green things, our wavelength shifting fibers to read out the liquid argon scintillation. And then you can get a bit of a closer view of what those detectors look like. So there's really not much supporting them. You'll notice we have the scintillating plastic. We have some low mass front end electronics connecting to our detector, and that's really it. We're interested in making these detectors kind of as good as they can operate in liquid argon without anything nearby. So here's another picture of kind of our low background materials. Maybe I'll mention some of the more interesting aspects of the experiment. These copper rods you see are what's called electroformed copper. So basically you plate out copper by electroplating onto big mandrels. This is done underground at SURF in South Dakota. And that's done to prevent cosmogenic activation of the copper. And then still underground, you machine that copper with like as little interruption as possible, because you really don't want to introduce contamination to your very pure copper. So all of that's done underground, and then we send it to our experiment as quickly as possible, where we clean it and deploy it, and to avoid the cosmogenic activation, which I think is kind of neat. That's it. Yeah. And then here's like our front end electronic, I guess. It's also really small. You can see that we have a small transistor, basically, which is the heart of the detector readout. Okay. So here's sort of some aspects of our detectors. And one of the big things I haven't mentioned yet that we use on Legend is pulse shape discrimination in our germanium detectors, which you're probably familiar with from other germanium detector experiments. But this is kind of the key part of Legend. So one of the features in our detectors that is a little bit different than other germanium detectors you might use for spectroscopy, for example, is that our detectors are so large that the drift time from these lobes of the detector is on the order of a microsecond. So they don't have good timing resolution, but they have really good pulse shape discrimination. So for example, if you have a gamma come in and Compton scatter in our detector, if we have charge clouds created at two different positions on our detector, just due to the drift time, we'll get a really good separation between those charge clouds. And we can see kind of the time scale in which those two charge clouds come in separately to our point contact, where we're reading out the charge. So that induced current signal gives us a lot of power to discriminate events where we have multiple sites versus like a two neutrino event where we expect all the energy deposition to be kind of localized in one small area. So this is really the powerful aspect of our pulse shape discrimination. We can also do a multiplicity cut because we have an array of germanium detectors. So if we have a gamma scatter in two different detectors, we don't expect that two detectors will pick up an energy deposit for a double beta decay signal. So if we see two at the same time, it's most likely an external gamma. And then I already mentioned our argon anti-coincidence cut. So if we see a gamma, for example, or a beta or something deposit energy in our argon, we'll know that that event is background. the other thing I'll mention is I mentioned our energy resolution is at 0.1% full half max. That is about 2.5 keV, even for these really large mass detectors, which are on the getting up to like 3 kilograms. So that's very heavy, you can imagine. Yeah, let's show the rest. Here's a little bit more on our pulse shape discrimination, just to sort of show you what our waveforms look like. So this is, an example of what a double beta decay event would look like. We use this, I don't think it's mentioned here, but we use this parameter called A over E. So this is like the current, maximum of the current divided by the energy. So our charge signal is in blue. If we take the derivative, that's our current signal. And basically, we expect kind of all of our events in the whole detector to be in some acceptance band in terms of like their peak current. And so this would be a double beta decay single site event. If we were to have a multi-site event from Compton scatter, for example, our current signal would look something like this, right? And so then we know that this event is very different from our double beta decay. So we would be able to reject that. And then there's other surface events on our detectors coming from, it's bare germanium. So we're actually sensitive to betas passing through our lithiated N plus contact, but their current signals look different. We're also sensitive. We have a very thin dead layer on our point contact. So alphas, for example, can penetrate, and we expect their signals to look different there too. So anyway, so to show you what putting all that pulse shape discrimination together, this is what our energy histogram looks like. So in gray is our histogram pre-cuts, right? And then once we apply our pulse shape discrimination, we get down to the green histogram. You can already see this is a really powerful technique. We're reducing our background by a factor of 5 or something around Q beta beta. We do really good at rejecting alphas that have high energy. And I'll show you later, but we're getting the 2 nu spectrum is looking kind of this sort of curve. And so we're actually doing really good in terms of rejecting our backgrounds, which is great. Okay. So the other piece I already mentioned is our liquid argon instrumentation. I won't go through the whole mechanism, but basically we have liquid argon scintillation. It goes through a number of wavelength shifts and then goes into these green fibers, and which transmits the light up to SIPMs, where we read out the number of photons, basically. And if we apply that cut as well, we do another factor of 5 or so in terms of rejecting backgrounds around Q beta beta. And now this red hump that you see here is really basically just the 2 neutrino spectrum with a few gamma lines on top. So this is really nice. Okay. So then that gets us to kind of the result I already showed you. This is what our final energy spectrum looks like around Q beta beta. And then we do a statistical inference on it. And then we got our combined results. So I mentioned already this combination of our predecessors plus legend, we get something that's about 1.9 times 10 to the 26 years half-life. And then in terms of M beta beta, it's down here in the bottom. And I already showed you kind of how that compares to other experiments and how it compares to the neutrino mass hierarchy options. So this inverted ordering versus normal ordering. And so the next generation goal is to cover the inverted ordering and rule it out in terms of this parameter space. Okay, so that's what Legend 200 looks like. Our first physics result, we have many more years of running, so we'll do even better in the future. But the thing that we're working towards now is also upgrading to the next generation experiment, which will be Legend 1000. So Legend 200 is up to 200 kilograms of germanium. Legend 1000 will be up to 1 ton of germanium detectors deployed in this more complicated experiment. And like I already mentioned, the goal of Legend 1000 is to probe the inverted ordering, so 10 to the 28 years half-life, and that will take 1 ton of germanium-76 for 10 years running with a lot of upgraded instrumentation, upgraded cuts, lots of interesting physics. I'll talk a little bit more about. So let me get to how ARUNA Lab, SENPA, is supporting Legend. So SENPA's accelerator is a little bit limited in its abilities. It's an FN tandem. We get up to 9 megavolts about, but we mostly run protons, deuterium, and sometimes helium beams. We're not really able to do many heavier species. We used to have a sputter ion source that hasn't been run in like 20 years. Needs a little bit of refurbishment. So this, in terms of our ability to directly probe like nuclear physics relevant for Legend, it's a little bit limited. But we are able to do sort of two isotope productions that we've recently investigated. And so I'll tell you a little bit more about that. The SEMPA tandem is really good at supporting helium-6 crests, which is this other really interesting experiment that you might have heard about, looking for fundamental symmetries with beta decays. Very, very cool. And then we also do some detector testing for other particle nuclear physics experiments that I won't touch on. So I'll tell you about these two isotopes that we did at SEMPA. Yeah, one we produced at SEMPA, this cobalt 56, and the other we've done a lot of prototyping here with for argon 42. I'll talk about. So you might ask, why is cobalt 56 interesting for Legend? And we use it as a calibration source. And the reason is that it has a number of double escape peaks that are near Q beta beta. So the double escape peaks are shown here with these gray lines. Q beta beta is shown up here in this blue line. You can see they're pretty close for what Legend would consider. And more importantly, it has a series of them spanning kind of this energy range. And these double escape peaks are interesting to us because they have basically the same topology as a two neutrino event. So in a two neutrino event, we have our two electrons coming out of the decay and neutrinos escaping or no neutrinos escaping. But most of the energy is deposited by these two electrons. If we look at a normal Compton scatter, right, we'll get some electron, some that has some amount of energy that deposits on our detector, and maybe that gamma ray could escape. In our double escape peaks, we pair produce an electron and a positron, and then the two 511s from the annihilation of the positron escape the detector. And so all of our energy deposition is really coming from this electron and positron. That's two leptons. It looks very similar to what we would get from a two nu event or a zero nu event, right? Those two electrons having most of the energy. So that's topologically basically the same as the events that we're interested in. And so therefore we can use those events to estimate things like our signal acceptance efficiency, how efficient are our cuts at rejecting background and preserving signal. That's an important parameter in terms of like the efficiency overall for Legend, which we use to go into our half-life limit. So that's the reason we want cobalt 56. It's a slightly difficult isotope for us to work with. It has about a 2-month half-life. That means it has to be produced on demand and sent to Legend. That process takes time. And because Legend is a physics experiment where we're deploying these detectors for years at a time, we have to plan things kind of far in advance. And so we have to align beam time for production of this cobalt 56 in line with like when we want to do these deployments for special calibrations. So that means that we only do this every few years. We need sources that have a high enough activity to get statistics for us, but not too much for our detector pilot, because I mentioned that we don't have great timing resolution. So that means we want something on the order of kilobecquerel is sort of the level we're talking about. That's tens of nanocurie if you're more used to thinking in terms of curie. Legend is more used to thinking in terms of micro and millibecquerel. So it's like different orders of magnitude in terms of activity. Special calibrations can't take too long, right? Because we want to preserve our physics data taking ability. So maybe on the order of a week or two, kind of at most. And I just show on a picture here on the right, a cartoon of like what a typical source deployment would look like for us. So we would have a few sources deployed along this meter array. You can imagine that the detectors very close to the sources are getting a lot higher rate than those detectors that are further away. And that means that we would prefer to have more weaker sources deployed more uniformly along kind of this string, right? So the last time we ran a cobalt 56 special calibration was a few years ago. This was not optimal just because we needed to produce these sources parasitically at another facility. So we couldn't optimize in terms of like how much activity, how many foils, that sort of stuff. And so we'd like to find a better place to do this cobalt 56 production so we can do more foils, more sources, more uniform activity, smaller activity, make them really more custom to like the needs that we have. And that's a great opportunity for the SEMPA tandem to come in. So I'll tell you about a test we did. So this is a very easy reaction, basically. It's an enormous cross-section for production, getting up to half a barn. It's just enormous. So it's also easy. We can do it with protons. So it's just a iron 56 foil or natural iron foil with proton beam at energies that are really achievable for the tandem here. And so we did this a couple of years ago now. Natural iron foil, not particularly thick or thin. We did this also parasitically with another experiment detector testing that was running here. And so we, irradiated our foil for 15 minutes, expecting an activity of about half a microcurie. And when we went and measured it with our own detector, that's basically what we got, was about half a microcurie of couple 56. So that's perfect. Even for legend, this is probably too much activity, but it's really easy for us to scale down the irradiation time to 5 minutes or even less. And we can also, our tandem is set up to have foil wheels. So it's easy for us to produce a couple dozen foils of whatever activity we want and ship them off to legend to be used as calibration. So that's great. We can, and because, in contrast to other like user facilities, the SEMPA tandem really isn't oversubscribed. And so it's very easy for us to schedule beam time whenever legend kind of desires us to make sources. So that's really nice. So not particularly difficult, but not previously considered for legend. So it'll be a big improvement for the experiment. And then I want to thank Sam Borden and our other graduate students, but Sam in particular, for thinking about this and making the steps to make it happen. So that's cobalt 56. Let me move on to argon 42. This is a much more challenging isotope to work with, both for legend and for SEMPA. So I'll tell you a little bit about that. So argon 42 is cosmogenic. It has a 33-year half-life. It's like we think it's most likely an alpha 2p reaction that occurs high in the atmosphere from cosmic rays. So argon 40 is the natural abundance. It's like, I think almost 100% natural abundance. But we get about 100 microbecquerel per kilogram in atmospheric argon. So in our big liquid argon cryostat that we're putting our detectors into, we have something like, I think, 90 tons of argon. And so we end up having kind of a lot of argon 42. Now, and the reason that it's a problem is that 33-year half-life, it beta decays with only 600 keV. So that's well below Q beta beta of 2 MeV. But the problem is this potassium 42 that it decays to has a 12-hour half-life and a Q beta of 3.5 MeV. So 3.5 is larger than 2, which means that some of these beta decays from potassium 42 are going to cover Q beta beta. And more importantly, we think that this potassium 42 is either ionized when this argon 42 decays, or it picks up some charge, and it ends up drifting or being convected to our detectors. And so instead of having like an isotropic distribution of potassium 42 in the large cryostat, we end up accumulating this potassium 42 on our detectors. And so originally, you might think that this really isn't a problem. This small activity is kind of distributed, but we end up being incredibly efficient at accumulating potassium 42 right on the surface of our detectors, which makes it a much bigger problem. So the predecessor to Legend, Gerda, realized this a long time ago. And the solution that they came up with was putting these what are called mini shrouds, basically these plastic sleeves that go around the detectors. And those plastic sleeves act to block the ion migration of the potassium 42 onto the detector. So that's effective at reducing our background a lot, but there's still some argon inside of these tubes. There still can be some convection that allows ions to kind of accumulate, and we still see potassium 42 as one of the backgrounds, which again is coming from this argon 42. Yeah. So that's sort of what our spectrum looks like. And the potassium 42 is this blue line. You can see that it covers Q beta beta, and it's sort of our second highest background pre-cuts. And I think something like our third highest background post-cuts at Q beta beta. So that's very interesting, I would say, and also a problem, especially for Legend 1000, right? If we have to reduce our backgrounds by a factor of 10, how are we going to, kind of eliminate this potassium 42 background? Well, the solution right now is, because this is cosmogenic from argon 42, we're going to source our argon from underground wells, where we've eliminated the cosmogenic production of this argon 42. That's kind of a risky endeavor, right? There's a well in Colorado right now that I think is hopefully turning on this year, if it hasn't already, that'll start this extraction of argon. But it takes a long time. It's with a commercial vendor, so there can be some risks. And so we'd like to study alternatives for Legend 1000 that can be, new shielding ideas, new pulse shape discrimination, or machine learning techniques to reduce this background further. So in order for us to do that in the lab, right, this is, I mentioned the activity is only 100 microbecquerel per kilogram, which is, basically impossible to measure on the surface, where our labs are located for like prototyping. We really need a high activity argon-42 source that we can spike our argon cryostats with in order to study these new techniques. So we need something like a microcurie of argon-42, which means we need a way to produce it. Okay, so here's expected backgrounds for Legend 1000. You can see here even with our underground source argon, there's a lot of uncertainty over how much potassium 42 is in that underground source argon, and so it might end up being one of our highest backgrounds, but still within the limits we need to reach. Okay, so here are some mitigation strategies I was mentioning that we want to study with argon 42. People have had good ideas about 3D printing some enclosures that fit tightly around our detectors. That will prevent a lot more argon or potassium 42 from migrating to the surfaces. And then these are scintillating plastics, so you get the light rejection that we need. That's very cool. We can also think about freezing the argon, which is a little bit more out there, seems a lot harder to do. How you're going to deploy detectors inside of frozen argon, I don't know. But all of these sort of strategies need a calibration source of argon 42 in order for us to work with it. So in the few minutes I have left, I'll try to explain what we're doing. So here are sort of 3 reactions to produce argon 42 that we're thinking about. There's a lithium-7 reaction. This is the way in the past that labs have produced argon 42. The difficulty is that if you want to really ramp up production to sort of microcurie levels, it's difficult to get high enough beam currents of lithium-7 at most facilities in order to do that. It's very easy to get alpha beams of really high intensities at something like cyclotron. So that's the technique I'm going to focus on. This is maybe not the optimal production. You happen to produce a lot of this argon-39, which is also a background. That's not so nice in terms of prototyping, but it might be okay. And then kind of a more out there technique would be to use tritium. So I think a lot of people are interested in tritium beams now. We're also interested for producing argon-42. This is nice because it has a high cross section. It's this pink line. And it's also free from producing argon-39, which has a higher turn-on energy. So this is a very nice production, but only a couple facilities are kind of developing that ability right now. So we're going to focus on the alpha beam for now. Oops. So none of these cross sections have really been measured. There's sort of one unpublished study that was done 20 some years ago that these green points kind of agrees with different predictions, but not great agreement. So just to point that out, if someone's interested in measuring this, it would for sure be useful. So sort of beam parameters. Okay, so basically for cyclotron, we'd be targeting something like a 65 MeV alpha beam, 5 particle microamps for a couple day irradiation. That gives us about 300 watts on target, which is kind of significant. We want the alpha beam to basically fully stop in the argon. That suggests that we want to use like a high gas pressure target or maybe a liquid argon target. I'll talk to you about the gas target we designed. And we want to have a high beam energy so we can sort of maximize our production of argon-42, right? Okay, so this is the gas target design that we came up with. Our design goals, we want to minimize the argon pressure. Obviously, having a high pressure target that you're producing a significant amount of activity in is kind of a hazard. So we want to minimize it, but we need enough to stop the beam. We really want to minimize the argon volume. That's because we'd like to ship this source elsewhere. So in order for us to do that, we need to make it in a shippable size for easy transport, radiation safety in terms of shipping. So we don't want to make too much. We want to minimize the energy loss in the window. That's because we have a high beam current. We don't want to put too much power on it, potentially melt it. and release this radioactive gas. That would be bad. And then, we want to minimize the heating, so we'll add water cooling basically and try to reduce the beam power on target that we really need. So we designed this at a working pressure of about 10 bar, which is about 150 psi. We fully pressure tested this up to like twice that. Good. The volume is kind of minimized. It's 180 milliliters inside of here. It's constructed entirely of aluminum. We've connected it. We're using like indium phase seals, VCR, to keep the already high purity, but mostly to prevent escape of radioactive gases. And then it's possible, most likely, that the beam, which is depositing so much energy inside of our argon gas, is going to kind of rarefy the gas along the beam path. And maybe for our next setup, we'll probably increase this a little bit. This is probably too much detail, but just to show you a little bit of some of like the calculations we did for designing the target. You can use SHRIM to study the range, straggling the materials, the window, the argon gas cell cross section, and basically what that gets us is we want something that's like 25 centimeters long. That's not too long to bring to a lab at 9 atmospheres, 9 bar, some inner diameter and entrance window diameter. This is what our window looks like. Maybe a little bit interesting. I'm sure you know that usually you want really thin windows in targets, and that's to prevent heating of the window, and also typically people care a lot about how much energy is being lost in the window. It turns out for us, we'd actually like a relatively thick window, and that's partially because we have to support so much pressure. And in terms of the heat load that we expect on the window, it's kind of a trade-off between the conduction in the window, which improves as you get thicker, so for heat mitigation, versus how much heating you have on the window. And so it's kind of even trade between those, and which works in our favor for having a high pressure gas target. So we're using 125 micron foil, which is thick for most like foil applications. It's pressure tested to 40 bars. So this is after pressure testing. You can see it didn't burst. This is way higher than the pressure that we'll need. So that's great. And we expect about a 15-watt heat load from the alpha beam that we're designing to. And that's something that we can test with our SEMPA beam, which I'll talk about. So very cool. This is sort of the expected temperature profile. You also have to think about, for aluminum, the maximum allowable working pressure of aluminum changes as a function of temperature. So we can't go too high or we're liable to put a hole in it from gas pressure from heating, basically. But this is sort of the temperature profile that we expect. The other interesting thing I want to mention is when we go to remove argon from the gas cylinder, you might ask, how do we do that? And the answer is we're taking advantage of the phase diagram of argon. So argon's freezing point is at a higher temperature than liquid nitrogen, which means that if we expose the argon cell to like a liquid nitrogen bath, bring down a gas cylinder to that temperature, the argon will be extracted from the cylinder or from the gas cell into the cylinder where it'll condense and freeze in the bottom of the cylinder. And so that's how we extract the argon, basically, is we just cool it down. If you look at the phase diagram though, so we're basically following this line where we go from the gas phase through the liquid phase into the solid phase. But this boundary line is telling us sort of what the vapor pressure of argon is when we're in the solid at like a liquid nitrogen temperature of about 78 Kelvin. And it's like 0.3 bar, which means that if we, is a relatively high fraction of the gas that we've irradiated would remain in the cell, which would be a hazard, and also we'd like better efficiency for collection. So the way to mitigate that is to flush it, introduce new argon into the cell, and then pull it into the cylinder. And if you do that enough times, you'll dilute the radioactive gas to a sufficiently high level, and basically have like 100% extraction of the argon-42 that we made. So that's great. So this is just a plot. You can sort of optimize that. Okay, the way that we do that is with this gas handling system. It's this collection of different valves that are actuated by a PLC system. I won't spend too much long on it, but it may be kind of interesting for people. This is like not a kind of off-the-shelf PLC system that's not very expensive, which is nice. More importantly, that's coupled to this slow control system called Slow Dash that's developed here at UW by one of our collaborators, Sanshiro Enomoto. This is a nice way to interface with the PLC system, have a human interface, read off gauges, and then you can sort of see here in the left, this is a screen showing basically the extraction. So this red line is the pressure in our gas cell from starting, and then we begin the extraction where we pull all the argon into our cylinder, and then we introduce new argon into the cell, and we do that about 20 times. And all that's handled by the PLC system, so it's automatic. It's kind of cool. I'll also mention that you can run this system on a Raspberry Pi, for example, if you wanted to read out and record gauges. So our student, Jan Ru, has done that. There's a link to his GitHub package if you're interested. This is cheap, it's fast, it's nice. You can do real-time plotting. It's very cool. Okay, so SENPA is not able to produce argon-42 ourselves. We don't have a lithium beam that's available. We can't reach the energy or beam currents we need for alphas. We can't do tritium. So instead, what we did here is we used the deuterium beam for a heating test of that foil I was mentioning. And also we produced argon-41, which has a 2-hour half-life. And we used to check the argon extraction to make sure it was working, basically. So there's a single gamma at a 1293 keV. If we, the idea is basically if you kind of measure the activity in the gas cell before and after extraction, you can kind of estimate how efficient it was, for example. And so we did that with the germanium detector. And then we're also, in this reaction, we produce a lot of potassium, some potassium-42. And I didn't mention it, but in this diagram here, there's a getter. And that's to collect reactive species, chlorine, potassium. Those isotopes are also produced, but we don't want them in our argon supply. And so we'd like to just make sure they get collected in our getter. And we ran this just a couple months ago in December. So this is sort of the setup. This is our gas cell. Here's our argon supply line just on the end of a beam line. We did 2 tests. One is we heated the foil with the beam to just see if we would melt it, basically. It looked totally fine, no indication of damage or heating. We did this with about 20 watts on target. We had a tiny Faraday cup because there wasn't an existing one at the end of the beam line. It was too tiny. And so this is sort of a screw holding it on that is completely melted. That should be not bent. So that's a lesson learned, but not a big deal. And then the second test we did was we added in argon gas to our gas cell in order to produce this argon-41. Here's kind of the cross section. So we irradiated for 2 hours. The beam energy after losses in the foil is down to about 2 MeV. So it's not very high in terms of like where the cross section looks like, right? Because we don't need to produce very much of it. And we aim to produce 15 microcurie of argon-41. After our 2-hour radiation, we waited for a cool down period of 30 minutes, and then we went in to make measurements, began the extraction procedure. This is the same plot I showed before showing what that looks like. Extraction went great. We noticed the activity was a lot higher than expected after our extraction. That was a bit of a surprise. And after we did some measurements, we realized we produced 20 millicurie before our cool down period, so after the end of the irradiation. So that's rather a lot more than we intended. I would say that's approaching dangerous levels. It's a good thing that we were aiming to produce kind of this lower activity, because originally I was targeting something that was a bit higher, like millicurie level. So it's really good that we decided to be safe and go aim for a lower one. We suspect that the cross section is probably really wrong. This is basically a factor of 1,000, right? So the only explanation we've come up with is that this cross section is not measured and it's really wrong. So lesson learned for us is we should have done like a 5-minute test and see what sort of cross section that we measured and expected, just to make sure that this is going to be safe. But luckily, all the systems worked as expected. We didn't have any issues. The tests we did, we really aren't set up to measure cross sections here or kind of other interesting physics. So if maybe someone else at an lab is interested, that would be an interesting project from our perspective, but not something that we can do here really. And then this is what the spectrum from argon-41 looks like, just to show you. It's really boring because there's a single gamma. And also you'll notice if you do gamma ray spec that this resolution looks terrible. This is like 60 keV full with half max. That's due to our detector, which was a pop top, not really working very well. We had a ton of pile up because we produced way more activity than we expected. And then, because we were kind of rushing due to, not wanting to be near this source for very long, we didn't really optimize the DAC settings. But it's good enough for the run, and we can get a measurement of the activity, which is mostly what we were interested in. And then the other thing I'll mention is that we identified potassium-42 in our getter and nowhere else. So that seems like it works really well. So that's great. So in terms of prototyping, our gas cell and our argon extraction work great. So the next steps for us is our cobalt-56 is kind of ready for SEMPA to produce whenever Legend needs it, maybe within the next couple of years. Our argon-42 prototyping went really well here. We're excited to do a run later this year at Berkeley with an alpha beam. And then we have some priority 2 beam time at Atlas, hopefully once they get a tritium beam operating, in which case we'll use a liquid argon gas cell. But we'll have to see if that runs this year, at some point in the future. The cross sections for these reactions are also not measured. So that's interesting in terms of maybe we produce more activity than we expect, which would be good, but we'll have to play it safe. And then just to mention again, Legend 200, we're still in data taking mode. For Legend 1000, we're in the design and planning phase. We're in the CD process. So I'm sure that you all hear a lot more about Legend 1000 in the coming years if you haven't already. And we have really exciting prospects for discovery of the neutrinoless level beta decay in the near future. So look for that. So let me just thank our local UW Legend group, our faculty, PI is Jason Detweiler, other faculties, Claudia Severese, postdocs, our graduate students who have done a lot of this work. And let me point out specifically Sam Borden and Clint Wiseman, who's one of our tandem operators now, who had the idea to look for an argon-42 production here at SEMPA. We have other faculty and staff who helped us, Alejandro Garcia, our tandem operators, our EHS staff, EHS staff, and then our external collaborators who have helped us get beam time at facilities. And then thanks to the Legend collaboration too. Sorry, I went a bit over time, but that's it.
No worries. Thank you. Great talk. Good highlight of University of Washington. And I guess we'll open the floor to any questions after everyone does a virtual applause.
I think yeah, well, thanks. I see we have a lot of Legend collaborators on, so they probably know everything. But
Well, I had a quick question. I was just curious with Legend, how frequently do you get to analyze the data? Do you have to wait till the runtime's over and collect?
that's a good question. So maybe I'll just look at a spectrum. So, for example, this gray region here is well, that's our blinded region basically. So the way that our analysis works is we analyze the data outside of this blinded region kind of all the time. We need to optimize our cuts. We need to, look at the detector performance, that sort of stuff. But we never look at the data in this blinded region until everything is sort of fixed, right? That's sort of typical for these experiments. So once we've optimized our cuts and we've fixed them, then we come together as a collaboration and we agree that we're ready to open the box and see what's inside, and then we do that. And that process happens every few years, I would say. So we basically want to collect enough exposure that we're kind of adding sensitivity to the next data release to the public, for example. So our first publication was at 60 kilogram years. Probably our next one will be when we collect 250 kilogram years, something like that. So that will be a couple, 2-ish years away, I would say, before we do our next data release.
Okay, thank you.
Yeah.
Hey, Louis.